Welcome back, Grade 6 to Nelson Math, Chapter 8, Getting Started. During this unit, we will identify relationships between and among linear and square metric units. You see in the word linear, the word line, so you're going to be measuring along a line. And square metric units, you'll be measuring counting squares. You will express area measures using more than one unit. Develop and use rules for calculating the areas of parallelograms and triangles, and you will determine the missing dimensions using area formulas. So you'll be given the formula and you can figure out what the area is. Let's do a little bit of review now from the past. Number 1, estimate and then measure the area of each polygon in square units. How close were your estimates? So because here it's in dots, we're going to measure and say that between every dot, so start point, end point, that's 1 unit. So if I looked at this whole structure, I could say from here to here is 1, here to here is 2, here to here is 3, and here to here is 4. So I have 4 units along the top. So my width is 4 units. And then to count how tall it is. So we can go from here to here, that's 1. From here to here, that's 2. From here to here, that's 3. From here to here, that's 4. So I have 4 columns, and each column has 4 squares. So if this was full, it would be 16 total squares, or 4 times 4. But it's not full. I'm missing some from here, I'm missing some from here, some from here, and some from here. So I know it must be less than 16. I don't yet know exactly how much less, but I know it's less. So we could say an estimate could be 12 or 13 or 14 or 15. We have to count it to find out for sure. So if my estimate is 16 squares, then let's see if we can get a little bit closer. Let's start by counting the full squares first. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 full squares. But now I can take the half squares. So this is 1 half square and another half square, that's 1. Here's 1 half square and another half square, that's 2. Here's 1 half square and another half square, that's 3. Here's 1 half square and another half square, that's 4. So we had 8 full squares, and then we add up all the half squares, we get 8 half squares or 4 full squares. So 8 full squares plus 4 full squares gives us 12 full squares, and that's an exact answer. So our estimate was anywhere from 12 to 15, and we were able to get that. Let's look at this one now. It's the same idea. Let's count full squares first. So we can say 1 square, 2 square, and then we have some other squares over here. So it looks like maybe another 2 squares, maybe 3 squares. So probably these 2 plus these 2 or 3. So we're looking at approximately 4 or 5 squares. Let's try this now. So if we count 1 and 2, we could say that's 2 full squares. But here I have 1, 2, 3 squares in this rectangle, but it's really only half of that rectangle. So half of the rectangle of 3 rectangles would be 1.5. So 1.5 plus this half is 2. So we can count this one to be these 2 plus these 2, so 4. The area of this one is 4. Number 2, calculate the area of each rectangle. Use the rule for area of a rectangle and show your work. So the rule for the area of a rectangle is height times width, or it could be length times height. You take this dimension and multiply it by this dimension. So we learned in the previous chapter, 30 times 30, we can do 3 times 3 is 9, and then we can just add 2 zeros or multiply it by 100. So our area here is 900 square centimeters. And we have this one too. So here our length is 45, our width is 20. We could do 2 times 45 is 90, and then we multiply it by another 10, so it's 900 centimeters squared. A couple of more review. Would you measure each area in square kilometers, square meters, square centimeters, or square millimeters? As awkward as this might sound, you could measure all of these in any of these units, but some just make far more sense than others. For example, 3A, a provincial park. A provincial park is enormous. It's the size of many neighborhoods put together. So for this one, we would use square kilometers. It might be thousands of square kilometers. If we use, for example, square centimeters, which we could do, it would be in the trillions, possibly more, of square centimeters. That's not very helpful. So we would use square kilometers. B, glass for a poster frame. Assuming our poster frame is going to be approximately 50 centimeters by 100 centimeters, give or take, we'd probably use square centimeters for this. But we could also use square meters and say it's about half a square meter. C, tablecloth for a picnic table. If it's a larger picnic table, it would probably be in square meters. Because if the picnic table, let's say, could seat 10 people, it's a very big table, then you would need enough tablecloth to cover the whole table, and there's an overhang on the end. And then D, a calculator screen. A calculator screen is typically very small. So for this, we would generally use square millimeters, but square centimeters would also work. It might, for example, be 3 or 4 square centimeters, but we could also use square millimeters. So if it's 3 or 4, let's say it's 3 square centimeters, we can convert that to millimeters, and it would be approximately 300 square millimeters. Those are the best choices. Number 4, the community center is adding a skateboard park. It will be a rectangle with dimensions of 45 meters by 60 meters. A model will be used to decide where the ramps will be positioned. The model has a scale of 1 centimeter represents 3 meters. A, what is the area of the skateboard park? For this, I'm going to write down some responses. So for A, the area would equal the length times the width, which we are told up here is 45 times 60 meters, like that. And now to multiply 45 times 60. You're free to do this any which way you like. A calculator for this is more than fine for this unit because I'm not looking to see if you can do this in your head. So 45 times 60 is 2,700 meters squared, and we'll make it meters squared. So that would be for this question. And if we do B, B is asking, what is the area of the model? Not what is the area of the skateboard park, but the area of the model. And I'm just going to write down this information again. So 1 centimeter on the model is the equivalent of 3 meters in our actual skateboard park. So we have to change these dimensions, the 45 to 60, into centimeters for our model that we would make. Now for this, you can use trial and error if you want. So you could make a chart that says 1 centimeter, 3 meters, 2 centimeters, 6 meters, 3 centimeters, 9 meters. That would work. You'll eventually get to the answer. However, we're going to do it just slightly faster. So we're going to change this. We know that we have to multiply 3 by 15 to get to our 45, like that. So we're going to say 15 centimeters. This is our model now. So 15 centimeters by 20 centimeters. And now we can check to see if this is accurate. So if every centimeter here represents 3 meters, 15 times 3 is 45. And then 20 times 3 is 60. So now our area for the model would be 15 centimeters times 20 centimeters, which is 300 centimeters squared, like that. And if a region of 81 meters squared is roped off as a waiting area, what will be the area of the roped off region of your model? For this question, it is much, much better if we draw a picture of it. And we want to draw a picture of it so we can see what an 81 meter squared picture would look like. So let's take our circle here, our square. That's a pretty accurate square. It's only a sketch. We don't have to make it too exact. So if this square here is 81 meters squared, we have to see what would the side lengths be for this. So our side lengths, let's put in some labels. Our side lengths here, if it's 81 meters squared, we need two numbers that multiply to 81. We could do trial and error, increasing slowly. So for example, is it 5 times 5? That's 25. So no, that's not right. Is it 6 times 6? No, that's 36. That's not right. We could keep increasing until we get to 81 meters squared, but I can tell you it's 9 meters squared, and I'll fix that squared in a moment. Rather, not 9 meters squared, it's 9 meters. So this length is 9 meters. So if this length is 9 meters, then this length must be 9 meters. So let's check that now. What is 9 times 9? Yes, in fact, it's 81. So 9 meters times 9 meters, this has an area of 81 meters squared. So let's go back to what we were given before. 1 centimeter represents 3 meters. So in our real skate park, it would be 9 meters. But if we are representing it on our model, it would only be 3 centimeters because every 1 centimeter represents 3 meters. So 1 centimeter is 3 meters, 2 centimeters is 6 meters, 3 centimeters is 9 meters. So this tells us that each side is 9 meters in real life and 3 centimeters in the model, this section here. So if in the model this is 3 centimeters by 3 centimeters, then the area that's roped off would be the model area, which in this case would be 3 centimeters times 3 centimeters, which equals 9 centimeters squared. And this is why models are so important. It might have been very tempting for you to say, well, it's already told us up here 1 centimeter represents 3 meters. So wouldn't we do the same thing here? And the answer is no, because here we're not dealing with meters. We're dealing with meters squared. So please sketch out whatever it is you're being asked to do so you could do a model and label some numbers, so it makes this work much easier to do. Thanks, everyone. Have a good day.